The COMET project is about using industrial robots for machining technologies. We all know normal milling machines, quite expensive, and what we are looking for is a more cost-efficient but still very reliable technology to machine high added value parts.
In the COMET project we plan to do the offline compensation together with Power Mill or with a tiered system. In the work package 1 we are developing the models, describing the robot's behavior, describing the deviation the robot has due to forces, due to its errors, compliance in the gears or backlash in the gears that the user would occur. For example, during machining he wants to reach a certain spot but he can't, the robot has a certain error. And we want to know this beforehand, model this and compensate so we reach our target.
So with DECAM robot interface, we are now able to reproduce in the simulation the errors we can see on the robot, the inaccuracy. And using the mathematics developed by BTU and from IPA, we are now able to compensate for all of this to create a correct toolpath that take into account all of these inaccuracies.
And as you have seen in some of the experiments we are doing, we work a lot with model-based approaches and feedback. But many of those experiments, for instance the calibration routines that end up in models, that can then be used also online but primarily offline. And the advantage with using it offline is that then you can simulate and predict often better exactly how the robot will move. Of course you cannot take up some unforeseen changes online, but you gain in predictability, I would say.
This is a little personal because I have in my past experience a period of work in automatic control. And it is quite clear that automatic control is the basic subject of this project. Force feedback, different kind of control loops that act together in different times. So you talk compensating disturbances, making different control systems to reach an objective. So it's quite interesting.
Yes, the good concept here is that we can predict what will happen on the real robot and compensate before running it. And that's, I think, a very, very strong point.
We have the modeling approach for these dynamic effects, and then they are used in two different ways. First, it's to just predict, okay, what happens if the robot has this or that deficiency, such as backlash in a few joints, and when does it harm the milling result? And there we have impressive results now that we can even visualize that in Power Mill.
I can see that in this project does not happen what sometimes might happen in other projects, that the partners go along their own line of development. The project is very well managed, and I trust that we'll reach the objectives within the short time it has given itself.
So what excites me is that we are succeeding in connecting low-level dynamic effects with high-level user aspects. And that is really the key to success, I think.
What really excites me is that there's a phrase once said by a very famous person, Even Bell, and that is knowledge is power, but enthusiasm is the switch. And I really see that in this project we have 14 partners involved with a lot of know-how, but especially with their enthusiasm we are making a big change, and it will work in the end after only 30 months of very hard work.